The focus of this tableau was on the introduction of a new kind of chance variable, a Poisson variable with a fixed positive parameter lambda. This variable takes values in the non-negative integers in accordance with the Poisson mass function with probabilities p of k parameterized by lambda given in the Poisson form. The form of the mass function is simple. It has got a unimodal character, so it rises and then decays. It has got a probabilistic center of mass, or more formally, an expectation, a weighted sum, which is precisely the parameter lambda characterizing the distribution. And it has got an expected squared deviation away from the center, a probabilistic moment of inertia, if you will, or more formally and correctly, the variance, also precisely lambda. And at this point, we've got a complete characterization of a new kind of chance variable. The listener who has been a little more adventurous and has tackled the dangerous bend segments will have seen that some elegant properties emerged from this basic characterization. So, one, a stability result that arose out of considerations of merging of independent traffic streams. The key result says that if x1 is a Poisson variable and x2 is another Poisson variable and they constitute independent trials, then the sum obtained by merging the two is a new Poisson variable and its parameter is the sum of the two individual parameters. Now, this stability observation was interesting in its own right, but was key in the development of the Poisson process, which tries to capture a sequence of random arrivals in time or in space. Right. So, formally, the Poisson process, viewed as a function of a time parameter t, is a process, a chance-driven process, which for every fixed positive value t gives you a number of arrivals, which is a Poisson variable with a parameter alpha times t. Alpha here connotes the mean arrival rate. Okay. The process is characterized by independent increments. What that means is the number of Poisson points, the number of arrivals in disjoint intervals, in disjoint regions, constitute independent trials. How does one characterize such a process? What is the underlying sample space? We saw that one way of doing this was to look at the inter-arrival times, and we discovered that the sequence of inter-arrival times which characterizes the process is a sequence of repeated independent trials, each trial conforming to an exponential distribution. What about the arrival times themselves? These connote the waiting times of the process. The time to the nth arrival, Sn, as we've discovered, is another continuous variable, chance variable, and it is governed by a gamma distribution. Now, at this point, we've got a rather complete understanding of the Poisson process and the kind of ramifications of the basic structure. Where does it arise? Well, we've seen a plethora of applications. The reader may well remark on the importance of historical accidents, serendipity, in the shaping of discoveries. The Poisson distribution was discovered by Simeon Denis Poisson originally as an approximation to a binomial distribution which arose naturally in the characterization of verdicts in jury trials. And the Poisson distribution then arose originally in Poisson's derivations as a curious little approximation. But this curious approximation went on to have a life of its own. And over the next couple of centuries, it became clear that this approximation of Poisson captures not just rare events as an approximation to a binomial, but stands in its own right as a critical component of something which captures random arrivals. And this then leads to things like waiting times, queues, congestion control, spatial processes, whimsically, for example, the distribution of bomb hits in London, or the distribution of stars in the firmament. Now this concludes Tableau 10 Part 2. At this stage, we'll take stock and go back to the questions that we raised in Part 1 of this Tableau when we talked about the binomial distribution and the setting of poles. The listener should go back to Tableau 10 Part 1, revisit and summarize the key elements of the binomial distribution and the polling applications that engendered it. This shall be the topic of our next Tableau. And at this point, we will turn to the fabulous limit laws which underlie probability theory.